What specific problem does the method proposed in your paper aim to solve regarding the transitions between modes of computation in transformers during training?
The method proposed in the paper aims to solve the problem of understanding the dynamics of the transient ridge phenomenon in transformers during training, specifically the transition from generalization to memorization. This is achieved by investigating how transformers navigate an evolving trade-off between loss and complexity as they are trained on in-context linear regression tasks with varying task diversity. The paper extends previous analyses by employing joint trajectory principal component analysis, PCA, to reveal the behavioral development of transformers and clarify how task diversity influences these transitions. Additionally, it models the transient ridge phenomenon through principles akin to Bayesian internal model selection, providing a framework to explain the observed shifts in computational modes. Ultimately, the research seeks to expand the understanding of these transitions and their implications for neural network development.
How does the proposed method or algorithm work? Illustrate step by step, including the components you introduce and their interactions.
The proposed method investigates the transient ridge phenomenon in transformers trained for in-context linear regression by analyzing the evolving trade-off between loss and complexity during training. First, we define a conditional distribution of sequences based on latent regression vectors, allowing the model to sample tasks from a nested multitask data distribution. Next, we train transformers on these distributions while monitoring their performance on out-of-distribution sequences, applying joint trajectory principal component analysis, PCA, to capture the behavioral development of the models. The analysis reveals that as task diversity increases, the transformers initially approximate ridge solutions before transitioning towards discrete minimum mean squared error (DMMSE) solutions, illustrating the dynamics of generalization and memorization. Finally, we validate our findings by quantifying the complexity of the solutions using the local learning coefficient, confirming that the evolving loss complexity trade-off governs the training dynamics of the transformers.
Can you come up with a simple yet illustrative example on the inner workings of the proposed algorithm, specifically demonstrating how the transient ridge phenomenon occurs during model training?
A simple illustrative example of the transient ridge phenomenon can be seen when training a transformer on in-context linear regression tasks with varying task diversity, M. Initially, with low task diversity, the model tends to converge towards a solution that minimizes loss but maintains low complexity, akin to the ridge regression solution. As training progresses and M increases, the model's trajectory shifts towards a more complex solution that approximates the discrete minimum mean squared error (DMMSE) solution, reflecting a transition from generalization to memorization. However, at intermediate values of M, the model first approaches the ridge solution before pivoting towards the DMMSE solution, illustrating the evolving trade-off between loss and complexity. This behavior is captured through joint trajectory PCA, which reveals that the model's function space trajectories are increasingly drawn towards ridge as task diversity increases, demonstrating the dynamics of the transient ridge phenomenon.
What are the theoretical or practical benefits of using your proposed method in understanding the transient ridge phenomenon compared to existing methods?
The proposed method enhances the understanding of the transient ridge phenomenon by modeling it as a dynamic trade-off between loss and complexity, which is grounded in the principles of Bayesian internal model selection. This approach allows for a qualitative prediction of how transformers navigate this trade-off during training, providing a clearer framework for interpreting the observed transitions between generalization and memorization. Additionally, by employing joint trajectory principal component analysis, PCA, we can visualize and analyze the behavioral development of transformers across varying task diversities, revealing the correlation between function space trajectories and the underlying computational strategies, DMMSE versus ridge. This method contrasts with existing approaches by offering a more nuanced view of the evolving dynamics, as it quantifies the complexity of competing solutions using the local learning coefficient. Overall, our findings suggest that this evolving loss complexity trade-off framework is a promising avenue for further empirical and theoretical exploration of neural network development.
How is the transient ridge phenomenon validated or tested in your experiments? Please elaborate on the experimental design, datasets, and metrics used for evaluation.
The transient ridge phenomenon is validated through a series of experiments involving transformers trained on nested multitask data distributions with varying task diversity parameters, specifically ranging from m equals 1 to m equals 2^15 and including m equals infty. The experimental design includes training transformers under the mean squared error objective and evaluating their performance on out-of-distribution OOD sequences, allowing for a comparison of their behavior as they approximate either the discrete minimum mean squared error (DMMSE) or ridge solutions. To analyze the dynamics of these models, Joint Trajectory Principal Component Analysis (PCA) is employed, which decomposes the collective function space trajectories of the transformers, revealing how their behavioral development correlates with the transition between generalization and memorization. The evaluation metrics include OOD loss on a fixed test set sampled from the Q_INFTYS distribution, as well as the local learning coefficient LLC to quantify the complexity of the solutions. This comprehensive approach allows for a detailed understanding of the evolving loss complexity trade-off that characterizes the transient ridge phenomenon.
What limitations or drawbacks have you identified in your proposed method regarding its application in observing the transient ridge phenomenon, and how do you suggest addressing these limitations?
In our study of the transient ridge phenomenon, we identified several limitations. Firstly, our analysis primarily focuses on in-distribution behavior, raising concerns about whether transformers can accurately approximate idealized predictors across all input sequences. Additionally, we noted that the solutions governing training dynamics may not necessarily correspond to the parameters to which transformers converge, suggesting a need for further exploration of mechanistic interpretability. We also acknowledged the simplifying assumption that lower-order terms from each expansion cancel, which may not hold true and could influence the evolution of the posterior, particularly for low sample sizes. To address these limitations, we recommend future work to investigate the detailed behavior of transformer solutions in practice and to deepen the theoretical understanding of lower-order terms in the context of internal model selection.